Hey everyone, and welcome. Has the chapter on the magnetic effects of electric current ever felt a bit tricky? Well, you're in exactly the right place. We're going to break it all down and make sure every single concept is super simple, clear, and easy to remember for your exams. Let's do this.
So here's our game plan for today. We're taking a four-part journey. First, we'll hit the basics. What even is a magnet? Then we'll figure out how to visualize its invisible forces. After that, we'll uncover the huge secret that connects electricity and magnetism. And finally, we'll learn how to build a way better magnet. It's a straight shot, so let's jump right in.
Okay, let's get into it. We're going to start with something we've all played with, right? A simple magnet. But have you ever really stopped to think about what's actually going on? What makes it tick?
At its most basic, a magnet is just any material that has this cool ability to attract stuff like iron, nickel, and cobalt. The classic example we're going to use today is the good old bar magnet. It might look like a simple rectangle, but it's got two super important ends, a north pole and a south pole.
Now, every single magnet out there plays by a few unbreakable rules. First, if you let one hang freely, say from a string, it'll always point itself north-south. Second, you've probably felt this one. Like poles, so north to north or south to south, they push each other away, they repel. But unlike poles, a north and a south will snap right together, they attract. And here's a big one. You can never, ever have a north pole by itself. They always come in pairs, a true package deal.
So if this whole magnetic force thing is invisible, how do we even know it's there? Well, our number one tool for the job is a magnetic compass. A compass is really just a tiny magnet that's free to spin, and its needle will always react and point in the direction of any magnetic field nearby.
All right, now that we know how to spot a magnet's presence, let's talk about its area of influence. Think of it like every magnet has its own invisible territory, a space all around it where its power can be felt. This is what we call its magnetic field.
So, the magnetic field is that region of space where a magnet's force is active. In physics, we give it the symbol B. And what's really important to get is that it's a vector. That just means it doesn't just have a strength, or magnitude, it also has a specific direction at every single point in space.
But come on, how do you actually map something you can't even see? Well, we use a clever trick. We imagine these things called magnetic field lines. Think of them like a roadmap for the magnetic force, showing us exactly where it's going and how strong it is.
These imaginary lines aren't random, though. They follow very strict rules. Outside the magnet, they always flow out of the North Pole and loop around into the South Pole. But inside the magnet, they travel from south back to north, creating a perfect, continuous closed loop. Where the lines are packed close together, the field is super strong. And here's the golden rule, the most important one of all. Two magnetic field lines can never, ever cross each other.
And that brings up an awesome question, one you'll definitely see in exams. Why? Why is it physically impossible for two field lines to intersect? What would even happen if they did?
Let's just think it through logically. Let's pretend for a second that two lines could cross at one single point. Now, what if we put a tiny compass right there, at that intersection? Remember, the compass needle has to show the direction of the field, so if there are two lines crossing, the needle would have to point in two different directions at the exact same time. And that's the problem, right? That's physically impossible. A compass can only point one way. So bottom line, field lines can never, ever cross.
Okay, now for the part of the story that literally changed the world. For the longest time, people thought electricity and magnetism were two totally separate things. But then, one scientist made a discovery that connected them forever.
This is the moment. A scientist named Hans Christian Ørsted was doing an experiment and noticed something weird. Whenever he sent an electric current flowing through a wire, the needle of a compass he had nearby would move. Now, what's the only thing that can move a compass needle? A magnetic field. The conclusion was unavoidable. An electric current creates its own magnetic field. Mind-blowing.
What an incredible discovery. But of course, it immediately opened up a new puzzle. Okay, great. A current-carrying wire makes a magnetic field. But which way is that field pointing?
Thankfully, there's a really simple but powerful trick for this. It's called Maxwell's right-hand thumb rule. Here's how it works. I want you to imagine grabbing that wire with your right hand. Now point your thumb in the same direction the current is flowing. Okay? Got it? Now just look at your other fingers. The direction that your fingers curl around the wire, that's the exact direction of the magnetic field. Simple, right?
So when you use that rule on a simple, straight wire, you find something really cool. The magnetic field lines form perfect concentric circles all around it, and the strength of that field is pretty straightforward. You pump more current into the wire, you get a stronger field. You move further away from the wire, the field gets weaker. Makes sense.
So we know a current can create a magnetic field. That's awesome. But can we make it better? Can we engineer this discovery to build a really powerful magnet that we can actually control? Oh yeah, for sure.
It's actually all about the shape of the wire. A single straight wire gives you a pretty weak magnetic field. But what if you bend that wire into a circle, a loop? Well, now the field lines start to get concentrated right in the middle, making it stronger. So let's take that to the next level. What if we take a whole bunch of loops and coil them up into a cylinder, like a spring? That's what we call a solenoid. And inside that coil, you get an incredibly strong and uniform magnetic field that looks almost exactly like the field of a bar magnet.
So, the official definition of a solenoid is just a coil with lots of circular turns of insulated wire wrapped up into a cylinder. But its real superpower, the thing that makes it so useful, is the field inside. It's strong, the field lines are parallel, and it's totally uniform. That means the magnetic field has the same strength and direction at every single point inside that coil.
So let's put them head to head, a regular permanent bar magnet versus our new electromagnet, the solenoid. With the bar magnet, everything is fixed. Its strength is what it is, and its north and south poles are permanent. But with an electromagnet, you are in complete control. You can crank up the current to make it stronger, or you can even flip its poles, make north become south just by reversing the direction of the current. And maybe best of all, you can turn it off. You have an on and off switch for magnetism.
But if you want the ultimate upgrade, here's the final trick. Take a piece of soft iron and stick it right inside the solenoid. The iron core gets intensely magnetized by the solenoid's field, and their two fields add together, creating a way more powerful electromagnet. This is the secret behind those giant magnets you see in scrapyards that can lift entire cars. So we've come full circle. We started with a simple toy magnet and ended up understanding how we can use an electric current to create a powerful, controllable magnetic field. But this leaves us with one last huge question. We've seen how electricity can create magnetism, but could it be a two-way street? Is it possible to use magnetism to create electricity? Now that is a thought to hang on to.